So I'm kind of describing my own toy project, which I've been doing for a couple of weeks. Um, and this also I did for my class project for a course that I did. And the inspiration is, I always got inspired from Apache Spark as to how it is able to specify a job and schedule it on multiple machines, multiple nodes. So it takes out all the complexity of specifying a distributed job and lets a user specify the job simply by describing the tasks that he wants to do. So simply like create a context, create a distributed data called RDD and doing something with it. And looks like a simple functional code, but finally it gets translated to multiple nodes to do a lot of work in parallel in a distributed way. And so that's the beauty of Spark. But Spark is able to do that because the Java objects are really serializable. So it's runtime, it's able to serialize the object onto a different node and then construct it back together to create a computation. With Haskell, that ability is not just there. So my goal was to be able to use Cloud Haskell, the machinery that is provided with Cloud Haskell, and create a component out of it really. So this is not really something that works with Apache Spark, but it works like Apache Spark. So if one wants to look at something that is written in Haskell but works with Apache Spark, so already there is a project called Sparkle, and that should be able to take care of creating Haskell job, putting it into kind of embed into a Java object and serializing it on the other side. I don't know if they do it, how do they do it, but they are able to do that. So the implementation that I had is really simple. So I based it on Cloud Haskell. I also used static pointers and remote tables. So that is for the polymorphic types. We'll come to that in a minute. And basically use a kind of a closure to spawn the process and job onto a remote node. So there is also an alternative available to it, and then I checked with developers of Cloud Haskell as well as there is another library called HDPH, and so HDPH is more or less it more or less conducive to work on the same machine and multi-core kind of a machine, whereas Cloud Haskell is really for distributed, and that is the advice that I got, and some also suggestions for the library that I have written. So essentially the static pointer is kind of a core with which it works right now. So and this is recently introduced into Haskell runtime, that a monomorphic type or a type with a type dictionary can be converted into a fingerprint, and that is called a static pointer. And there is an extension called static pointer which enables one to convert a function. Suppose we have a function like square, and it's possible to convert that square into a static pointer, and then it's nothing but the fingerprint, 128-bit fingerprint, which now can be serialized, put it on the wire, and can be coerced into a function back on the other node if it is there. Right now the implementation is unsafe, but they promised that in next version of compiler, I think it's already out, the implementation would be quite safe to use. But this is not sufficient for all the purpose, because this is not able to take care of polymorphic types. The polymorphic type is handled a little bit differently in Cloud Haskell. So what Cloud Haskell does is something clever. It takes a polymorphic type and converts into a dynamic type. So for example, if you have a type, so say if a function is say a to b, then the dynamic type would be like any to anyone, and that any to anyone would be a typeable and dynamic, which latter can be coerced into A and B, different types. So, and this dynamic type is kind of registered into a remote table, and this table is actually exported onto multiple nodes wherever we want to run Cloud Haskell worker. So, if we want to run with or create an application with Cloud Haskell, we can use both static as well as dynamic types or remotable types. That is what Cloud Haskell says, and in fact combine them together and create a serializable object which can be serialized on the wire, and it's possible to spawn something on the remote node as well. So it's very clever as to how we can combine them together. So if you can create a closure, the closure can be a static extension itself, or it can be a remotable extension. So if you have a closure, and if you have a closure of certain data, then it's possible to construct a higher level closure of B by combining closure of A to B and closure of A. So, and it's possible to create a higher level object, something like a context which needs to be run on the other machine. Oops, I just locked. Okay. So this actually looks like a. I'm more familiar with Actor in Scala and Akka, so it actually inspired from Erlang, but I cannot talk about it because I don't know much about it. So the process is a bit like based on a transport layer. A transport layer can be TCP, it can be, in fact, they have multiple layers for like, they also have a layer for Azure or something. But typically it's a transport layer. Each process has a queue to process a message, and process itself is a finite state machine which can be in any of the state as described by the message handler. And a node is nothing but a container of process. So node is a logical, you can say, container. So on the same process on your machine, you can have multiple number of nodes, or node can exist anywhere in the network. And now using the closure that we have, it's possible to kind of create a spawn something on either locally or on the remote node. So now using all this machinery, it's possible to create a simple DSL to specify similar language that Apache Spark has. So this is little bit about internals of Sparks, like, and how I visualize it for my application. So some processes are like, for example, if you apply functions like filter, map, then really speaking, whatever data it's coming, you are just filtering it and passing it on to the next process. But processes like folding or reducing, that is where the data has to go from multiple nodes and processes to multiple nodes. So shuffling occurs between when map reduce, the reduce step happens, not when map step happens. So it's possible to optimize the filter and mapping step and combine them together. But when we go from mapping step to reducing step or reducing step, then there we have to do a partitioning, and that partitioning in Apache Spark happens with some kind of default range partitioning or hashing. So basically I applied, I kind of asked the user to give the hashing function. So for me it was easy to do that. And so what I did is I tried to create a strategy application which lets specify the distribution strategy on the multiple nodes, and then I also kind of define blocks as a set of processes which can hold the data whenever it is ready. And the heart of the application would be to create a type class called RDD, which would define a function called flow, which would take in the context, take the base RDD and create a process which can be on any of the nodes. That so block is nothing but set of processes which can be anywhere on the network. So it creates a process which can spawn multiple processes. And using this, now it's possible to define multiple data types, such as, so for example, this is the map data type, which essentially takes a function, a closure of a function, which defines a kind of data pipeline, which takes the base RDD, just like Spark does, and it's able to handle it using the internally defined flow along with that. So here is an implementation of mapping RDD. So it typically happens in a standard way. So it calls the execution of the base. So it's like always pull kind of a system. And then it handles and creates own processes on the by equally distributing the work on the nodes that we have in the network. And that is how it's able to work with the mapping function. So these are some more details as to how map would be instantiated. So that's an internal detail. So finally, when we have different RDDs implemented, so it's possible to write the application in almost similar way that Apache Spark allows. So here is a very simple example to create a list from 1 to 10. Now seed that on multiple nodes by dividing it into set of partitions, map it with set of function and reduce it by having two functions. One is combining, which is kind of a fold, distributed fold, and a partitioner, which kind of a hash, which allows it to distribute the data on multiple nodes, so that the collect, when it wants to collect it, it knows where to ask the data for. So the additional things you would see a lot of places where an extra type parameters or type dictionaries are passed. That is required because I need to qualify the type, and then it's kind of a dictionary trick in Haskall, and it's a pretty standard trick in which, it's possible to embed a type class, type dictionary, and pass it around the network. Execution in this is very simple. It's rather ridiculously simple, in which it tries to distribute the data equally and doesn't try to see the pressure and the workload for each node. So that is how it is done. So basically it uses process as both as a computation, as a placeholder where you can ask for data from the parent process, and also to deliver it to the child process. In fact, whenever it delivers the data to the child process, it also exits and kind of prunes itself. So same way we did the mapping RDD, reduction RDD actually happens in two steps. The first step is reduce locally, and second step is to partition and then distribute the data on multiple nodes. And then again locally do the reduction step. So of course, like this is not a Spark, obviously. How can you do it in a few weeks? But I'm kind of glad because it works, and I kind of tested it with multiple nodes, multiple machines that I had. Unfortunately, doesn't always work on Windows. In fact, also because Cloud Haskell is probably not very well tested on Windows, but it works kind of well on Mac and Linux. So I also put the responsibility of creating the execution on the RDD itself. So my own the work that is going on is to create a acyclic graph instead of creating the flow directly, and then it's possible to create a error correcting kind of processing by basically giving a resiliency to the whole process. Some few things are already happening, like serialization on local node is already optimized in Cloud Haskell. And if it's possible to add, there is also already a Mesos kind of a library for Haskell. If it is possible to take that, then the orchestration framework can also be directly there, and it's possible to spawn the multiple nodes also at the same time. Right now there is some limitation because Haskell TCP layer doesn't do very well to identify the nodes in the network. So that's it. So this is the work that you can go to. So it's there on my GitHub repository if you want, and that's it.